So let us recall what we have did in the previous lecture. In the previous lecture, we have discussed regarding the phase transition. So when you have the isolated vertices, then the phase transition is 0. When is a forest of a tree or a component of a size greater than of big O of log n, when the value of P is of this much. What does it mean of a phase transition and a threshold value? So for that we need to understand this, that is Pn is a value which we want to say that it is a phase transition, threshold value. If the P1 upon P is equal to 0, where this G and P1 at most surely does not have that property, and P2 upon P is tending to infinitive as n tends to infinitive, then G and P2 has at most surely have that property. Then we can say that the GNP graph model or any random graph model has a phase transition, and this P is called the threshold value. Now, what do you mean by the GNP graph model at most surely does not have that property? That means the probability of having that property goes to 0. And n tends to infinity as n tends to infinity. And then there is a two types of properties are there. One of them is increasing property and another one is decreasing property, and some property are neither increasing nor decreasing. That also we can see. And then we have discussed regarding the SAP threshold. SAP threshold is the threshold P where C into Pn. If C is less than 1, then graph does not have that property. If C is greater than 1, then graph has that property. And then we have discussed regarding the first moment and the second moment. To discuss the first moment, you have to prove that this expectation of x is the number of items occur in the graph. That item might be anything, you can take it. For example, it is having the triangle or having the isolated vertices or having the Hamiltonian cycle, whatever the things you need to take. If the probability of x is greater than or equal to 1, if the expectation is tends to 0, then we can say that by Markov's inequality that the probability of x is greater than or equal to 1 is tending to 0 as n tends to infinity. And that method is known as first moment method. Now, in the second moment method, you require your x will be a random variable with the expectation is greater than 0. And the variance having the relation with the expectation is this. That is, variance of x is a small o of e square x, where x is at most surely greater than, then we can say that x is at most surely greater than 0. And that method is known as a second moment method. We have proved the second moment method in the previous lecture, and also we have discussed this corollary where the expectation of x square having the relation with expectation square is this, then also we have a same output. With this, today we'll discuss regarding the a threshold for graph having diameter 2, or it is another way is says that degree of 2 degree of separation. So first of all, you should understand what does it mean of diameter. The diameter is the a graph is maximum length of shortest part between pair of nodes. The diameter of a graph is the maximum distance, maximum length of the shortest path between pair of nodes. So that is known as a diameter. So here we are just we are not trying to prove that theorem, but we'll see that the first example of a phase transition of the property, that is the diameter is 2, means they slightly increase the age probability p near to threshold. It takes from at most surely not having that property to at most surely having that property. The property is that at most surely not having is less than or equal to diameter 2. In other words, what we are trying to see is the property that every pair of nodes had at most 2 degree of separation. Every pair of nodes have at most 2 degree of separation. That means you pick up any two vertices in that GNP graph model, then the maximum length, or I can say shortest distance, will be maximum 2. So we'll discuss this technique for deriving the threshold for graph having the diameter 2 is the standard method often used to determine the threshold for many objects. And that method is the first moment method and the second moment method. Let X, so we are discussing what is the procedure. So I'm just denoting X is equal to the random variable for number of objects such as you can just say that as we have discussed in the previously, it is triangles. So it is number of triangles, or you can say number of isolated vertices, or you can just say it is a Hamiltonian circuit. For which you want to determine the threshold, whatever the property you can take. Then we determine the value of P, let's say P0, where the expected value of X goes from vanishing small to the boundedly large value. For P is less than P0, at most surely graph is selected at random will not have a copy of them. And for P is greater than P0, a second moment argument needed to establish that the items are not concentrated on vanishing of small fraction of a graph, and that graph picked at random will at most surely have that property. Now, to discuss this threshold for diameter 2, our first task is to figure out what to be count to determine the threshold for graph having a diameter 2. A graph has a diameter 2 if and only if, what I can say in another way is the for each pair of vertices I and j, either there is an edge between them or there is another vertex to which we can both I and j have a edge. So if I want to prove that, so it is says that a graph has a diameter 2. So I can say if and only if there will be two situations. Every pair of edge is I and j is there. So either they are connected by an edge, or there is another edge, so another vertex k which is in between I and j. So this situation, either this situation is occur or this situation is occur. Any one of them is there. So if a graph has a diameter 2, if and only if for each pair of vertices I and j, either there is an edge between them, or there is another vertex k to which both I and j have edge. So I'm just saying that is this situation. So what we will count the number of pairs I and j that fails this situation. That means number of pairs I and j that have more than 2 degrees of separation. So ultimately we need to count that a graph has diameter 2. So it is equivalent to saying that every pair of vertices, either they are connected with one edge, or there is some another vertex which is in between them. So here is the length is 1, and here it is the length between this two is 2, and every pair of vertices satisfying this, then we can say that it is a 2 degree of separation. But while the calculating this, what we are doing in the reverse process, that means a contradiction to this statement. That means, so if we want to count the number of pairs which are failed to this, that means the number of pairs I and j that have more than 2 degrees of separation. The set of neighbors and the set of neighbors of I and j, a set of neighbors of I and j are random subsets of expected cardinality NP. And for this interest, we require that this NP will be equivalent to root n, or I can say that P will be 1 upon root n. In such statement often go under the name called the birthday paradox. And this is not actually a paradox, but it follows, and we will going to see that the threshold for is square root of ln n upon n. This will be the threshold for the graph having the diameter 2. And the extra factor that square root of ln ensure that every one of the pair NC2, because there are two vertices I and j you have to select out of n, so that's why there's a possibility NC2 pairs will be there, has a common neighbor. And when p is equal to this c into square root of ln n upon n, for c is less than square root of 2, then the graph at most surely has the diameter is greater than 2. And if the c is greater than root 2, then graph at most surely has a diameter less than or equal to 2. So that means the square root of 2 into square root of ln upon n is the sharp threshold for a graph having the diameter 2. So this is the actually theorem which we have discussed here. The proof is very interesting to see. The property that GNP has diameter 2 as a sharp threshold at p equal to square root of 2 into square root of ln n upon n. So this is the things which we have. To see the proof, I suggest that you can go to the your reference book, that is Foundation for Data Science by Blum, Obskroff and Kanan. You will find the very interesting proof of this theorem, and once you do it, you realize that, or you see the procedure, what will be the things you can have.